So hello everyone, in this video we are going to talk about oscillation, oscillatory equation essentially. So basically the theory of oscillation. So what do we have? First of all, we are starting in the last lecture we have seen that let's say you given a equation which looks like this: P0 x y double prime plus P1 x y prime plus P2 x y equals to 0. Let's say you are given this equation, right? Now we know that there exists a function, there exists sigma x, let's say, such that if you multiply, let's say 1, such that sigma x times 1, okay, let me write it down, that times the equation 1 will convert 1 into a self-adjoint equation, convert 1 into a self-adjoint equation. I hope you remember that, self-adjoint, right? Okay, so you see basically what I am trying to say is this: given any equation you can actually convert it into a self-adjoint equation, right? So from now on I am only going to talk about self-adjoint equation because those are very nice equations. I will tell you why that form is very important. Okay, so consider the equation this. So from now on I am going to consider this particular form. Consider this equation: P of x y prime whole prime. If you remember, this is the self-adjoint form, right? Qxy equals to 0. Yes, and so we'll look at this problem. Let's call this problem as 2, and if Px is identically equals to 1, okay, then this equation looks like this: y double prime plus Qxy equals to 0. Qxy equals to 0. Okay, so this is 3. Okay, when Px is essentially 1. Yes, so here we assume that P and Q is in C1 of I. Okay, whatever interval I it is defined on, it is C1, so continuously differentiable. This is what we are assuming essentially. Yeah. Okay, so you see here in 2 and in 2, of course, you see if P is C1, y prime is continuous and differentiable. See, y is C2, right? For any solution of this is at least twice continuously differentiable. So y prime is continuous, okay, and it is differentiable. So P is differentiable, y prime is differentiable, so I can talk about the derivative. So all of this makes sense, okay, right? Now, okay, now definition. What do we mean by oscillation? So a solution y of x, okay, solution of what? Let's say solution of this equation 2 of 2, clear, is said to be oscillatory, okay. So we are calling the solution as oscillatory for now, okay, if it has no, okay, last 0. Is this okay? Last 0. So what it means is, that is, let's just put it this way, that is, if y of x1, let's say, if you can find a x1 such that y of x1 is 0, then there exists a x2, okay, which is greater than x1, such that y of x2 will also be 0. Is this okay? So this is when we call the solution as a oscillatory solution, okay, and 2 is called oscillatory. See, the solution is oscillatory if there is no last 0 of the solution, and 2 is called oscillatory if all solutions are oscillatory. Is this okay? Are oscillatory. I hope it is clear here. See, if all solutions are oscillatory, then we call the equation as oscillatory equation. Yes, and one solution, if you are just looking at one solution, that is oscillatory if it does not have any last 0. Very clear, right? And of course, if a solution, if you have a solution y of x which is not oscillatory, we will call it a non-oscillatory. So that's just nomenclature, right? So let's look at an example. See, consider the equation. Consider y double prime plus y equals to 0. Clear? So you see, any solution y of x will look like this: c1 times cosine x plus c2 times sine x. And this is valid in whole of R, right? Whole of R. And do you think there is a last zero? Of course not, right? Because sine and cosine, they may have, I mean, if you take any solution. So basically, let's say any solution of this y1 of x, let me put it this way, this will become more, I mean, it would be sine x. These are the two linearly independent solutions for this problem, and they form the basis for the solution space. So basically, and you can see that all solutions, so this solution doesn't have any last zero, this doesn't have any last zero, right? So basically the combination also, you can actually see that there is no last zero. So basically what you can say is this is an oscillatory equation, is oscillatory. The equation itself is oscillatory, okay? Right. Now A, but if you change the sign a little bit, y double prime minus y equals to 0, then you see that the solutions y1 of x you are going to get is exponential x, and y2 of x what you are going to get is exponential minus x. None of them has any 0. So it is non-oscillatory. Oscillatory. Clear? Okay. So now the thing is this: we want to prove a result which is like a fundamental result in this direction. Okay. So this is called. So essentially the idea is this: see, as we have seen that for a variable coefficient equation, yes, even linear. Okay. So let me put it this way. Remember this: linear equations are easy to solve if they are constant coefficients. Are easy to solve if they are constant coefficient, if the coefficients are constant. Clear? Now if the coefficients are not constant, they are not easy to solve. They are not easy to solve if coefficients are variable, right? Now in the last videos we have seen there is some way of solving it, like, right? If you can solve the adjoint equation, and then of course you can do it, but generally speaking it is not also easy to solve adjoint equation in most of the cases. Okay, so in those cases we want to know if without solving the equation we can actually deduce something more out of the solution of the equation. Clear? So in this direction, the first fundamental result which we are going to prove, and this is one of the most important results in this course, this is called Sturm's comparison theorem. Comparison theorem. Clear? So what does it do? It actually compares. Compares with what? We'll look at it now. So let's say if alpha beta in I, okay, some interval I, see I can be R also, but some interval I, are the consecutive zeros of a non-trivial solution. Okay, of course non-trivial solution, because if it is trivial solution, then everything, I mean every number is a zero, right? So it doesn't matter. So we are looking for a non-trivial solution. Yx, clear? Of, please remember this thing, we are talking about this equation 3, not 2, 3. Okay, 3. For now let's just look at 3, and then we will talk about what happens in 2. And if q1 of x, okay, is continuous, there is a function q1 such that q1 of x is continuous, and q1 of x is greater than equal qx. Is this okay? Okay. Of course they are not 0, so they are not equal, okay, in alpha beta. They are not equal but q1 of x is greater than equal qx. For some points they may be equal, but generally they are not equal. And see, since both are continuous, see q is this, okay, since both are continuous, if they are non-zero at one point, they have to be 0 in some neighborhood of that point, right? Okay, so that is the only assumption. Then what you can say is, then every non-trivial solution zx of y double prime plus q1 of x times z equals to 0 has a 0 in open alpha beta. Okay, fine. So let us understand what it is saying. You have two equations, y prime plus px or qx, in this case qx y equals to 0, and you have another equation, y double prime plus q1 of x y equals to 0. Let's say you have a solution here. Let's call that solution to be y, such that y at the point alpha equals to y at the point beta equals to 0. So basically it's a 0, right? Now what this is saying is this: see that between alpha beta, if there is, these are consecutive alpha betas, there is no other 0 of alpha beta, right, other than alpha beta, then there exists a gamma between alpha beta such that any solution of this, okay, every non-trivial solution, you see, any solution of this, of course not the 0 solution, but any other non-trivial solution, let's say z is any other non-trivial solution, z of gamma will be 0. That's what it is saying. So the bigger coefficient, okay, is actually forcing the smaller one to actually give up a root. Let's just put it that way. So you will you remember this. You see, the smaller coefficient has two consecutive zeros. Then the bigger coefficient will have 1 0 in between that. Clear? Okay. So let's look at the proof. The proof is not very difficult. So what you do is this. So first of all, maybe, okay, so multiply, let me write it, otherwise it may get confused. Multiply y double prime plus qxy equals to 0, this equation, with z of x, clear, with z of x, and this equation z double prime plus q1 of x z equals to 0 with y of x, Is this okay? Now once you do it and subtract, you know, this is the exact same thing which we did while we did use the Lagrange identity, if you remember from the last class. Okay, so once you do that, what you have is z y prime minus y z prime whole prime, okay, plus q minus q1 y x zx equals to 0. Okay, how do you get this? This is exactly the Lagrange identity, if you remember. This is Lagrange or Green's, whatever you want to call it, doesn't matter, but anyway, so exactly the same thing. I mean, if you just take the integration part, then you can call it Green's, but anyways, it's okay. So this is the Lagrange identity. Okay, the proof of this we did it in the last class, so I am not discussing this part. Okay, now once this is true, now you see y at the point alpha equals to y at the point beta equals to 0. This is given, right? Consecutive zeros, you remember? Then integrating, what you get? Integrating, one has you integrate this thing, what will happen? You are going to get z at the point beta, y prime at the point beta, minus z at the point alpha, y prime at the point alpha. That is what remaining, because you see what happens to y at the point alpha, y at the point beta, that is becoming 0. So those terms are not there. This is the only term which is remaining. And then integral of this particular thing. Okay, so plus alpha to beta q of x minus q1 of x y of x z of x dx. I hope this is clear. Very simple. Okay, Lagrange identity. After that you integrate that. This is basically the Green's identity, if you I mean if you want to call that. Okay, so we have this. Now you see, the thing is, what we are going to do is we are going to use the linearity. So basically we assume that y prime of x is positive in alpha beta. See, this is where we are using the consecutiveness. See, essentially what we are saying is alpha beta, y is 0 here, y is 0 here. These are the consecutive zeros. So basically it can either do this or it can do this, any one of them. Okay, so we are just assuming it is positive. You can assume negative also, it doesn't matter. Okay, this is okay. So basically, let's say if it is positive, this is alpha beta. What is y doing? Y is 0 here. So it is going up somewhere and then it has to come down and match here. That is beta. Here. Okay. So y, so we are assuming y at the point x is positive. That's what we are assuming, huh? In open AB, y at the point alpha, y at the point beta is 0, y is positive in open alpha beta. Okay, then what happens to y prime at the point alpha? This is strictly greater than 0. Okay, why? So what I want you to do is this. You see, you do realize that it has to be increasing, right? So y prime at the point alpha, you see, y prime at the point alpha should be greater than equals to 0, right? See, it is increasing, it can be greater than equals to 0. Okay, so but the thing is, but that is not the case. Y prime of the alpha has to be strictly greater than 0. Why? Because if y prime at the point alpha is 0, and it is also given that y at the point alpha is 0, that is our assumption, that will imply y of x is identically equals to 0. This is Picard's existence uniqueness, right? Picard's existence uniqueness. This is the only solution. Okay, that actually violates the fact that y is a non-trivial solution. That's what we assumed. So this has to be true. Okay, so similarly we can also show that y prime of beta has to be strictly negative. Clear? So if that is the case, you see, now if let's say, what we have to show, I have to show z has a 0 in between alpha beta. If it is not the case, so if let's say z is positive in alpha beta, then what happens? Then let's call this a star. Then from star, what do we have? See, y prime of beta is negative, z of beta is positive. So this number is going to be negative. Again, z of alpha is positive, y prime of the alpha is positive with a negative sign. So this whole term is going to be negative. Is this okay? Right. Now let's look at y. Y is positive. This is what we assumed. Y is positive in alpha beta. What about z? Z is positive in alpha beta. What about q minus q1? Q of minus q1 is going to be negative. Is this okay? See, q1 is greater than equal q. That's what given to us, right? So what does it mean? It means that alpha to beta, q of x minus q1 of x, okay, y of x, z of x should be y prime at the point alpha, z at the point alpha minus z at the point beta, y prime at the point beta. Okay, this is the case, and this, you see, this y prime at the point alpha, as I already explained, right? So this is greater than equal 0. This is greater than equal 0. But q minus q1 is negative. Is this okay? You see, q minus q1, this is negative, right? Because it is given. You see, q1 is greater than equal q. So q minus q1 is less than equal 0. This is negative. Y is positive, z is positive. So this is a negative term, and that the integral of a negative quantity, basically we are writing that is going to be positive, right? So this cannot happen until unless, see, y and z, they are non-trivial. So until unless q is identically equals to q2, q1. Okay, but that is also not the case, because you see, we say that this is not identically equal. Okay, so hence our assumption is wrong, and therefore every solution, every non-trivial solution, z of x of y double prime plus q1 of x y equals to 0 has a 0 in alpha beta. I hope this is clear. Okay. So, and by the way, the very important theorem, this is a Sturm's comparison. So, please remember this thing. Okay. So, let's do a quick corollary of this theorem. It says that if qx, okay, is greater than equal 1 plus epsilon by 4x square, okay, epsilon positive for all positive x, then y double prime plus qxy equals to 0. This equation is oscillatory. Where is oscillatory? In 0 infinity. Is this okay? So basically what I am saying, what we are trying to prove here is this. So y double prime plus qxy equals to 0, right? That's the equation given to us. Can we say whether this equation is oscillatory or not? What is the condition? Okay. So this actually gives us the condition that qx has to be greater than equal 1 plus epsilon by 4x square. Okay. Okay. Where did we get this thing? Let's just understand that. Let's look at the proof. Now, I am not going to do the whole proof. What I want you to do is, I am going to leave some gaps. I want you to fill those gaps up. So, for epsilon greater than 0, okay, let's look at all non-trivial solutions. You see, all non-trivial solutions of y double prime plus epsilon by 4y equals to 0 are oscillatory. Right? This is trivial, right? Cosine sine. Yes, the solution. So they are going to be oscillatory, no problem. Okay. Now, define this this thing, change of variable. So t equals to e to the power x. E to the power x in this equation, y double prime plus epsilon by 4y equals to 0. Okay. If you take this change of variable, we have, you can actually convert it as a function of, from function of x to function of t, and that will look like this: t square y double prime plus t y prime plus epsilon by 4 y equals to 0. Is this okay? Now again using the substitution, y equals to z by root t. Okay, we obtain z double prime of t plus 1 plus epsilon by 4t square z equals to 0. This is what we get. Okay. Now, since zt equals to e to the power x by 2 y as a function of t, so e power x, this equation is oscillatory, right? I don't know how to put it, maybe double star is oscillatory. It has to be, right? Because this equation is oscillatory, so every solutions are oscillatory. Y is oscillatory, so every solution of this is oscillatory. Now I changed it to the another equation. Now for this equation also it has to be oscillatory, because z is e to the power x by 2 y power e power x, and y is oscillatory, so z has to be oscillatory, right? Therefore between any two solutions of this equation, what is the equation? This equation star. So therefore between any two zeros of which one, the this equation of star star, okay, there is a zero of every solution of y double prime plus qx y equals to 0. I hope this is clear. Yeah. Okay. So therefore the equation, see, q is greater than this, so you understand what I am trying to say. So therefore the equation y double prime plus qxy equals to 0 is oscillatory. Sturm comparison, right? Oscillatory. Okay, so this is fine. Now the thing is this, suddenly the question is this, why did we change it like this, and what is the main motivation of doing all this? Okay, let me just clarify. First of all, this expression t equals to e to the power x and changing into this, if you have a equation like this and if you want to change it to this sort of equation, so basically the equation, first equation doesn't contain any y prime, you have to check that. First equation doesn't contain any y prime. You see, this is the change of variable. If you did one second, sorry, if you did your Cauchy-Euler equations, you know that this change of variable actually converts this equation to that equation, the e to the minus x change of variable. Okay, so basically we are doing this in a inverse manner. So basically if we are taking t equals to e power x, then we can change this thing to t square y double prime plus t y prime plus epsilon by 4y. Okay, so this expression, this change of variable is coming from the Cauchy-Euler form. Okay, fine. Now you see, what we want to do is basically this problem again we want to write it in terms of another function. Okay, I mean this sort of function z double prime plus a function, let's say q1 of t times z equals to 0. We wanted to write it like this, and to do that what we are going to do, we did is this, y equals to f of t times z. This is the substitution which you took. Now once you do it and f is smooth enough, okay, you see I am giving you an idea, you have to check this part, f is smooth. Now you see y prime exists, y double prime exists, you have to find it in terms of f. Once you find it, you put it there, okay, and you assume that you will have some coefficient, so you will get some equation, right, with z double prime, z prime and z. The coefficient corresponding to z prime, you make it 0. Okay, when you make it 0, then you get f of t, which is 1 by root t. This is the idea. Is this okay? So once you get it, now why do we need this form? Why do we need this particular double star form? Because then we can use your Sturm comparison principle to get our result. I hope this is clear to you. Okay. Now let's look at some examples also. Let's look at some example. See, and this example, how do I put it? Let me put it in red. I am going to use this example in a lot of different places in this course. Okay, so I want you to understand this example. Maybe you can also find some questions in your assignment and in exams also corresponding to this particular example. Okay, right. So the differential equation y double prime equals to 0 is non-oscillatory, right? Non-oscillatory. Why it is non-oscillatory? Because any solution, because you see any solution of this problem yx looks like ax plus b, right? ab is in R, some constant. Okay, it will look like this. So you can see that these, there is only one zero, so it can't have like infinitely many zeros kind of. So it is non-oscillatory. Thus, if qx is less than equal 0, clear? Yes, and not identical equals to 0, of course, in I, whatever I is, I. Then Sturm comparison theorem, that will imply, this is a small one, right? Okay, that y double prime plus q of x y equals to 0 cannot have more than 1 0. Imply that no, each solution, I should write it, imply that each solution of this equation cannot have more than 1 0. Is this okay? Why is that true? Let's look at it. Again, I am not writing it, I want you to check it yourself, but I will tell you why. See, what happens is this. Let's say y double prime plus qxy equals to 0. This has two roots, alpha beta. Qx is less than equal 0, right? So basically, if there are two roots, consecutive roots, two roots, then in between those two roots there is another root of this 0 thing, right? Because qx is dominated by 0, Sturm comparison principle says that then y double prime equals to 0 will have one root in between. Is this okay? But this cannot happen, right? See, this yx equals to x, that one solution may have root, but you see yx equals to, let's say, 1 also solves this problem, right? But that solution doesn't have any root in between alpha beta. But what does Sturm comparison principle say? It says that every solution of that equation will have one root in between. So, but a constant solution is not going to have that root. Clear? So, it is this equation y double prime plus qxy equals to 0 is non-oscillatory. Please remember. Again, let me put it in this way. Very important result. Y double prime plus qxy okay, maybe I can put it this way. Q, let me give an example of Q. So let's say x square y, yes, equals to 0 is non-oscillatory. You can say that, or I can take it to be p, doesn't matter. So qxy equals to 0 is non-oscillatory, provided qx is less than equal 0. Is this okay? And of course not equals to 0. Is this okay? It's non-oscillatory. Very, very important result, and we are going to use this result a lot of time. Okay, this is first example. Now let's go back to our original thing. The second example is this. See, the equation y double prime plus y equals to 0. See what we are doing. If you look at it carefully, you see we are implying something about the solution of a variable coefficient equation using our knowledge of solutions for a constant coefficient equation. Constant coefficients we know how to solve. So those solutions we know how it behaves. We are using that behavior to give us what is the behavior of the this sort of solution. Clear? Okay. The equation y double prime plus y equals to 0, that is oscillatory. This we know. Oscillatory. Okay, so that will imply that y double prime plus 1 plus x times y equals to 0, okay, is what? Oscillatory or non-oscillatory? Think about it in 0 infinity. This is, I want you to check what exactly is this. See, think about it. 1 plus x is always greater than equal 1 in this interval in 0 infinity, right? So what can we say about it? So any solution of this, will it have a 0 in between? Y double prime plus y, any solution is oscillatory, right? So what can we say about any solution? So here, let me just put it this way. You will have oscillation here, okay? But please you do it yourself. Think about it, why it is true. Is this okay? Right. So yeah, this is fine. Okay. So now what we are going to do is going to prove a very important theorem, which is called the Picone's theorem, and we are going to video here, but before that let us just do the Picone's theorem first. So Picone's identity, Picone's identity again, the identity which I am proving now, Picone's identity, it may look like a very crazy kind of thing. I mean, you may get the idea that how are you getting this thing, and so, but what is the use of it? This is, let me tell you, this is a very, very important identity as far as this OD is concerned. But in PD, this is like a very, very vital identity. Okay, there are a lot of things which you can prove using Picone identity. Very important. Okay, so we are just doing it the OD part of that. Okay, so first of all, let the functions. What are the functions? Y, Z, P y prime, P1 z prime, okay, be smooth. Smooth means C1. Smooth means C1. Clear? And z of x is not 0 in I. Clear? I is some interval I. You can put any interval you want, doesn't matter. Then the following identity holds. Okay, let's look at what is the following identity. It says y by z, z p y prime minus y p1 z prime whole prime. This particular quantity is y. Now, please understand, there is nothing to understand in this. This is just some technical identity, okay? But it is very, very useful to prove theorems. That's what we are doing. Y p y prime whole prime minus y square by z p1 z prime whole prime plus, and you do not need to remember this identity also, so don't worry about it. We are just going to use this to prove this theorem, which we will call as Sturm-Picone's theorem. Very important. We will do it in the next video. Minus y by z, z prime whole prime. This is okay. So how do you prove something like this? The proof, it's a no-brainer basically. What you do is you break it up and then put it together. That's all. Okay. So what we are going to do is I'm going to start with this right hand side. So we have this expression. One second. Sorry, let's write the left hand side and we'll go to the right hand side from there. Okay, that will be better because it is just an expansion, right? So expanding the right hand side, what do we get? Expanding the left hand side, one gets y by z, right? Z p y prime whole prime plus z prime p y prime, okay, minus y p1 z prime whole prime minus y prime p1 z prime. This is what we are getting. Okay, I don't need that. This is what we are going to get, plus y prime by z minus y by z square z prime, z p y prime minus y p1 z prime. This is what we are going to get when we expand it, right? Now see, this is nothing but y p y prime whole prime minus y square by z p1 z prime whole prime, right? Okay, plus p y prime square, okay, and one second, let me just check it is okay, right? Yeah, fine, yeah, minus this part, one here, so 1 y prime p1 z1 y prime, this part and that part, so basically 2 y prime p1 z prime by z, that part is there, plus another by z square, that part is there, right? So basically this one z square part, so y square, what do you have? Y square, one second, let me just check. Y square p1 y square p1 z prime square by z square, that's what we have. Okay, yeah, this is fine. Okay, So now you see we are already here. So basically what we have is y p y prime whole prime. This is this y square by z p1 of z prime whole prime plus, now I will just write it like this, p minus p1 y prime square. Is this okay? Plus p1 y prime minus y by z z prime square. See, this is equals to this. I did not do any calculation because I know this is going to this. So please check this part. Okay. So this is the end of the proof. With this, I am going to end this video.